Okay, so in this presentation, we're going to look at facial recognition and how machines can make sense of faces. Okay, so we'll do a little bit around biometrics and what biometrics really are, and then how we map a face, and then going on to how we detect emotions, sadness, happiness, and so on. And then finally, we'll look at how we can detect faces using a cognitive engine. Okay, so let's briefly touch on biometrics before we look at facial recognition. So the thing about biometrics is that we need something that will identify a human. So it could be knowledge that is passed, such as their password, but it might also be something about the characteristics of the person. So we need something that is universal and that is applicable to most users. We need something that's unique. So your face is fairly unique, but your fingerprint is also unique too. Along with this, we need permanence, so that the feature that we take for biometrics does not vary too much over time. There's collectability, so how collectible is the biometric information. Performance, of course, in that we need to look at the accuracy of the biometric capture, the acceptance, whether a user might find a biometric method acceptable or not, and then there's obviously circumvention, and that relates to how easy it is for someone to trick the system. So here are some of the things that we might look at. So these are features of a human: their age, their weight, height, gender, hair colour, the DNA, their smell, and so on. But it can be quite difficult to detect these and to identify them as part of our biometric systems. So for this, we're looking for something that is distinctive, that is fairly easy to capture, and something that the users would trust. And irises themselves are fairly unique. The freckles and the shape of the eye and so on is something that can identify a user. But one of the best is to be able to shine infrared light into the eye and to look at the vein pattern on the retina. As we'll see, face recognition is one way to be able to detect a user fairly uniquely, and it's increasingly used. Ears also are fairly distinguishable. One method that's fairly accurate is in the vein pattern inside your finger, and you find that is fairly unique for most users, and it doesn't vary too much. For that, a biometric system might shine infrared light into the finger and then look at the vein pattern inside it. Handprints too are fairly unique, and the line patterns that we see, the length of the fingers, where the knuckles are, and so on, is also fairly unique in terms of defining a user. Fingerprints, as we know, are obviously a method of identifying a person, but gait too, and the way that we walk, is actually also fairly unique. Okay, so there are many different methods that we might use for biometrics, but in this presentation we will look purely at facial recognition. Okay, so there's a few things that we need to account for in terms of biometrics. A false acceptance rate, and so that's the times that the user will be identified falsely on the system. The false rejection rate is the percentage of times that identifies a target user as an imposter. There is also a receiver operating characteristics, and that's a trade-off between the false acceptance rate and the false rejection rate. And then we have the equal error rate, and that defines the point at which the false acceptances become equal to the false rejections. And then finally, we have authentication accuracy, and that really identifies a user correctly, both in terms of imposters and legitimate users. So let's look at facial mapping. Increasingly, our face is used to be able to detect users and for logins. So a mobile phone is often used these days, especially for Apple devices, to be able to scan the face and to be able to log in to a range of systems. So in this case, we might have a facial recognition, which is identifying different systems, and to be able to log in using a facial recognition plus a PIN number, or facial recognition plus a fingerprint, and so on. And if there's one thing, then your face, if it's possible for systems to match your face to these biometrics, then you can see that companies might be able to cross-reference your identity from one system to another. So the ways that we could detect a face include the size and the shape of the eyes, the nose, the cheekbone, and the jaws. And it might also be possible to create a three-dimensional mapping of the face to understand the general structure of it. Along with this, we might look at the skin, elements of the skin, the patterns, spots, freckles, age lines, and so on. And these will give us a fairly unique mapping of the face. So here's an example here. So what a machine will try to do is to be able to measure the distances involved in various points on the face. So in this case, we might measure the width of the nose, the width of the mouth, the width of the eyes, the height of the eyes, and so on. And it's these features that will be able to be matched onto what is expected from someone's face. But obviously, if a camera is taking a 2D view, then the distances will vary depending on how the head is rotated. So the machine must make some judgment as to the angles that a face is at, and then to scale those onto some form of measurement that could be compared against. So facial recognition often works by firing little infrared dots from a phone. And in this way, the infrared dots enable a 3D mapping of the face and a fairly accurate representation where it's possible to measure the angle that a face is at. And it'll be a three-dimensional angle. So we will have a rotation, and then we could have the head moving up and down. Okay, so on your phone, when you log in, then the phone is the imaging system on the phone is really trying to make these measurements. Okay, so what happens is that initially for facial recognition, a photograph, say, the machine will scan a photograph to be able to detect a face shape. So that's typically a rectangular face, and it will be looking for maybe the signs of a brow or eyes or a mouth. Once the face is detected, then it is then possible to do a feature finder. So in this case, there'll be some sort of scanning for eyes, mouth, nose, eyebrows, and so on. And then after that, the distances between each of these elements can then be computed and then stored for each user. So here's an example here. So we have Barack Obama. So we can see here that it's a fairly clear picture and the face has been detected in this region in here. And then these are the mappings for the eyebrows. The green identifies the eye, the yellow here for the nose, and then the blue for the mouth. And we can see it's managed to trace these pretty well. So over here we'll see the rectangle, and then these are all the elements that the machine has determined for this here. Along with this, we'll see things like pitch, roll, yaw, gender, facial hair, and so on. And really the machine is trying to sort of look at these parameters and then try to make some sense of them to match up to what it would see on its database. So let's try this example here. Okay, so if we take our image here and process it, this is what we get back from the system. So here we are here. There is the green is the eye, and we can see here it's done that fairly well. So if we try another one. Okay, so we can see even though the head is slightly offset there, it is still managing to find most of the features in the face. Okay, so we want to be able to get a representation such as this and to be able to map that. So what it does is to look for edges and lines. So in this case, the edge features that we're looking for is in terms of the hairline. And then we might be looking at the edge on here. So there are two main edge detections. We can see a horizontal and a vertical edge in there. Along with that, we look at line features. So in this case, we're looking at a line which defines the mouth, where it might go from light to dark to light again. But in other places, we might look for a dark area followed by light and then dark again. Okay, so we can see here that what we get is basically edge detection. When it comes to eye detection, very much we're looking for this dark, light, dark, where we see the nose in between, and then we see the eyes as darker areas. Along with this, we will get our face detection, and then in this case we have eye detection. The main method that we use is the HAR feature-based cascade classifiers, which was created by Viola and Job and Jones. And in this case, they define these XML filters. And these are filters which allow certain features to be traced. So in this case, we have a face detector and we have an eye detector in here. Then once we can import the face, and what we do is we typically convert it into a grayscale image, because it's easier to detect the different lines if we use a grayscale. And this is basically detecting any of the faces that we would have with inside the image. Okay, so let's give that a try to see if we can detect a face. And there we go. So it's managed to detect Steve Jobs' face there. We'll try John Travolta. Okay, so it's not getting that quite right. It's detecting two eyes there. It's detecting the general face region, But you can see here, there is a face behind him. It's also detecting that one too. So even in blurred faces, we can make a good attempt at detecting the face. So let's see if we can get some code to be able to look at this. Okay, so we have some Python code here, and it will integrate with our filter. So in this case, we're taking Obama here. So we have some pre-prepared images here that we can process. So we have Jimi Hendrix, Obama, and Steve Jobs. And we can just then process these for the detection of eyes and also for face detection. Okay, so this is the code that we have in here for face detection. And what we'll do is we'll just run that code and see how we get on. So here is the XML file here for the eye detection, and then this is for the facial detection in here. Okay, so let's run that file, and it's saved it to JPEG 111, and we can see here that's a pretty good capture there, because it's a strong picture photograph, which is obviously quite close, and it's easy for the system to detect. So let's try with Jimi Hendrix this time. So we'll just change that one. So we'll just comment out this one, and we'll take Jimi Hendrix this time, and we'll apply our two filters to it. Okay, so we have this one here, our Clint Eastwood photograph. This is a PNG that I had there. That's the reason that one didn't work there. So if we take Clint Eastwood this time, so let's see how that's processed. And you can see it's not quite as good as the last one. It's certainly detecting the face quite well, but because the eyes are not quite in the same place, it's detecting two eyes in here, but generally it's getting it right. If we try one more, we'll try steve.jpg here, and we'll just comment out that one there, and we'll bring in this JPEG. Okay, so that's worked there, and then this time we can see it hasn't detected the eyes in this case, so we'd have to probably change the filter and the way that the eyes were actually detected, but it's generally detected the face quite well in there. Okay, so there are some parameters that we can actually use to be able to enhance the detection in there too. Okay, so that's the type of code that we can use to be able to detect faces and eyes. But often what we want to do also is to be able to detect emotions. So the emotion might be happiness or sadness or depression, and the machine can actually start to look at the way that the face actually moves, so that it might be able to say detect aggression at a protest, so that activists could be detected before they caused trouble. So here are a few here. So what we see here is emotion. So this is sadness or a little bit of neutrality in there. And when we process this one, we can actually see that the neutral is fairly high, and probably the sadness is also high there. When it comes to anger, we can see this is an angry person here, and the anger is getting a score of 1.0, probably because the mouth is open, and the eyes are wide open too. In this case, we see happiness, and the person is smiling there. So there are other emotions: anger, contempt, disgust, fear, neutral, neutrality, sadness, surprise, and happiness, of course. So let's try a few of these to see if we can actually detect this. So we'll go for a contempt photograph here. Okay, so I don't know how good that is, but we can see it's scoring a little bit, 0.012 here, a little bit of happiness in there too, but a lot of neutrality in that face. If we look at surprise, so we'll feed in surprise, so that's definitely a surprised look in there. And what's coming back is surprise is 1.0. So you can see this is detected pretty well, a look of surprise, and none of the other scores are even getting a score there. Happiness, as we saw before, gets a good score here, and we can pick those ones off there. So generally this is happiness score of 1.0 there, so it's a very happy looking picture. So machines can really detect our emotions, happiness and anger, contempt, surprise, disgust, and so on, just by the way that our face will change. So for example, for smile detection, if someone shows their teeth, then that can be a pointer towards a smile. If the edges of their mouth goes up at the end, the cheek fold is another thing. The wrinkles in the forehead can identify anger, and where the brows are lowered. So there are various things, and there's actually a scoring system called FACS that will actually try to identify different types of emotions. So in this case, AU6 actually defines the cheek raising, the cheek going up, and then A12 looks at the lip corner puller, where someone will create a smiley face from there. Okay, so those are attributes of the face that can be mined for the emotion. So an important factor in this is pitch, yaw, and roll, and it's to do with the way that the face is positioned when the photograph is actually taken. And obviously, if it's a 3D photograph, then that's easier to be able to determine at what angle the face is pointing at. And this will be a 3D angle. So we have yaw, pitch, and then roll will define the angle at which the face is pointing towards the camera. So if we had a 45-degree angle, then obviously the distances will actually change for the measurements. So the machine must take that into account and then scale from, say, a 45-degree angle to a face-on picture. And we do that by dividing by the cos of the angle that we actually find. But if we look at 3 dimensions, then this is the formula that we'd use for the pitch. That's the y coordinates, the yaw is the x, and the roll is the z. So in this way we can actually nullify the effect of a face looking in another direction. Okay, so here's the example here that we saw before, and we can see here that it's fairly straight on, but there's a 9.7 degree angle detected for the way that the face is pointing. And then obviously when the machine is making a judgment, it will then have to scale depending upon these angles that we detect. But we can see also that the machine is looking at hair colour and various other things. So one thing that we need to understand is that obviously facial recognition could be used as a massive spying network. So are we moving towards a brave new world, or a world where we can log into our bank account using our face? So this is an example here where in real time it's possible to be able to detect the real-time emotion using a cognitive cloud. So in this case, the video can be uploaded in real time to a cognitive cloud, and in real time it can actually detect the emotions within the video. So it's possible to also detect in real-time emotions. So in this case, this is an example of how a video can be fed into the cognitive cloud and then in real time detect the changes in emotions. So this is one example here. So we can see here that the happiness is strong here and not so much for the other ones. If we take another example, we can see here that there's quite a lot of neutrality in here because of the straightness of the mouth from there and a little bit of sadness. You can see here quite a lot of anger in the face as it's been detected. So the machine can actually try to make sense of these images as they come through. And if we try to give even a cartoon character, it doesn't detect the face at all. And there's another one, we can see a little bit of contempt in there, a little bit of disgust, and so on. So the machine itself, the cognitive machine, can actually try to make sense of these photographs. Okay, so here's the example here in real time. We see here the happiness goes down, there's a neutral, and then the happiness comes back again. So the cloud, the cognitive cloud itself, and the machine can actually start to make sense of emotions almost in real time, as we see in this example. It can also look at two images and detect whether it's the same person in here. So you can see here the confidence level that the cognitive cloud has given us is that these two faces are 0.72 confidence that they're the same person. Here's an example here, and they're not the same person, and it goes down to 0.359 for its confidence. And the code that we're using here is the Microsoft Azure Cognitive Engine. For this, we need an API key, and once we have an API key, then we can call up using a post with set parameters and send the images up to the cloud, and then it will give us back the scoring system that we get. So in this case, when we connect, we'll get a response back again, and then from the response we get a JSON file. From the JSON file we can parse off and determine the scores for the images. And this shows an example here of a school in China where the children's faces are detected as part of monitoring the school roll. Okay, so that's been an introduction into facial recognition. Thank you.